You like that I was talking? That's good. It was nice. And it'll be nice for the next 5 years as I use that video. Everyone will be like, who's Erica? This one, it says the graph that best represents y equals ab of x when a is less than 0, b is greater than 1 is. Okay. Let's just hold up for a second and recognize that this is exponential. Agreed? That's an exponential function. Our basic exponential functions, if you think way back, we often drew them like this, with arrows on the end. That showed exponential growth, which was what most of our examples were involving. It was something getting bigger. Beautiful. That, like mother function, would represent this y equals a b to the power x, where a is positive, so a is greater than 0, and b is growing, b is greater than 1. That's our basic function. A is greater than 0 means I'm talking about like positive numbers, right? Almost all of our questions were a was greater than 0. I don't think we really did any that were negative. And then b is greater than 1 meant we had growth. So it looks like this. Beautiful. They now want to know, what would that function look like when a is less than 0 and b is greater than 1? So the difference between what we're used to seeing for an exponential and what they want to see for an exponential is they are changing a. A is going from positive to negative. Essentially, what they've done is they've taken your basic function. There's our basic function, f of x, and they've made it negative. They're saying take this, but have a negative a instead of a positive. Take your function and make it negative. When you take a function and you make it negative like that, we're doing a reflection. I'm running out of space over there. Let me pop over here. If you have something like this, your function but negative, that represents a reflection about one of the axes, either the x-axis or the y-axis. About the x-axis. Good job. All right, that's what a negative in front of your function does. It takes this, it reflects it to the other side of the x-axis, like mirrors it. So my new function, if I had a negative in front of it, would look like this. It would be a mirrored image on the other side of the x-axis, right? We called it reflection about the x-axis. Looking at our answers here, the answer would be D. Now, realistically, if I got to a test and I did not realize that they wanted me to do reflections, because it's kind of a messy reflection question, what I would have done is I would have just chosen a value for A that was less than 0. I would have chosen a value for B that was greater than 1, and I would have graphed it. And I want to try to figure out what it looked like. So anytime you get a situation like that, where they're like, okay, you have to follow these rules. A is like this, B is like this. What's the graph? Just make up an equation and graph it, and it'll look like one of those things. For instance, if you said A was -2 and B was -3, and you graph that, it would look like this. Oh, sorry, B is positive. It's greater than 1. There you go.
Wait, why did you just put a 2 in?
I'm just choosing values. So like just choose any value that follows these rules. And if you put those in, you'll get like a general graph. It looks like one of these. You'll notice that it looks like this. And you pick anything. I could make a -5. It would still look like this. I can make B6. Still look like this. Right? It's going to make this pattern. That's how I truly would do the question. What they were trying to get at was, do you recognize that this is a reflection? That's what they're trying to get at. But like test time, we don't always, have our best thinking cap on. So a backup strategy helps. That's a good backup strategy. Like just test numbers, see what happens. Cool.
Can you talk a little about exponential form? Like what? I forget about what that is. Sorry.
That's all good. It's been a while. It's a good little review. Exponential form, like this.
Like how you would convert.
Convert to what?
Non-exponential form.
To log form?
This. Like -f.
Like where'd that f come from?
Yeah.
Yeah, this is like what we were talking about earlier. Like where's that f of x keep coming from? Yeah, let's just back up for a second. Like what this means. Like that has infinite meaning. All that means is that y is equal to something that involves an x. That's all that means. So when I say y equals f of x, it means y changes depending on what x is. I don't know how it changes. I'm just saying it does change. Somehow y and x are related. That's all this is saying. And then I can define it. I can be like, that function, the way that they're related, f of x, they're related like this.
Oh, and then because y equals function of x.
Yes.
Function of x. That's basically just y equals ABX.
Yes.
That makes sense.
Yeah, it's the exact same stuff, right? And there's still going to be probably a dozen people in the room who are like, I still see what you're saying. But when that moment clicks, you're going to be like, oh, okay. I see what you're saying. This means y. Right? And it's the same thing. So this could be y equals ab to the power of x. The reason they use this terminology is because remember when we defined what a function meant and it had to pass the vertical line test? I'm saying this passes the vertical line test. That's why it's written like that. That's the only reason that it's written differently than just y equals. And then if I go and I'm like, all right, change it to be like this. I'm saying, go to your function and put a negative in front of it. This is what my function equals. Put a negative in front of it. So negative f of x would look like this. And that kind of concept. Negative f of x would be this. I just put a negative in front of the function. And where it gets confusing is then we say instead of using f of x, we call it y. All right, this is negative f of x. That's the negative of my function, which is this. Function notation is messy. Looking back, I wish we spend more time in Math 10 just talking about function notation in general. Because usually in Math 9 Math 10 always says f of x means y. And we just go with that the rest of your life. And then you get into this and it's like, what is he talking about? Why are you doing things to the function? And then why is it changing everything else? What's going on?
So then if you were going to say that b was negative, how would that be reflected in the function notation?
You couldn't do that in your function notation. You could make x negative though in your function notation. Yeah. So if I did this, if I was like, now take your function, this is my function, and I want you to make x negative, then I would go to the original function and I would make x negative. That's all that means. Go to the original, change x to be negative. It's trippy. Like, I get that. Like, it's honestly the hard part of function notation. The math's not crazy. What is crazy is like, how do you write things? Our last example is actually like perfect for right now for this conversation because it uses terminology that's like challenging. It's hard. So it says the graph of f of x equals that. This is f of x. Perfect. Is transformed into this. The equation that represents g of x is. So we're trying to find what g of x is. Are we okay with like what the question is asking me? What is g of x? Yeah, perfect. To find g of x. G of x has gone through a transformation. It's gone through this transformation. Those two negatives mean something. Visually, what's happening, if I had a graph, that negative is a reflection about the x-axis. Apparently I didn't put an N in reflection, and the I and the O are just one word now. Visually, that's what's happening. Visually, this negative means reflection about the y-axis. So if you had a picture of it, what I did was I took my graph, I reflected it to the other side of the x-axis, then I reflected it around the y-axis. So it's moved all the way around, right? That's essentially what's happened. Okay, they don't give us a graph, so we can't do anything about that. But it's good to understand what those two negatives are doing and what they mean. Mathematically, what they mean is that you take your function, this is my function, 4x squared plus 3x minus 5. That's my function. There's two things happening here. Thing number one is in red. This negative means take your function, 4x squared plus 3x minus 5, and multiply that whole function by negative. That's what the red negative is doing. It's taking the entire function and it's putting a negative in front of it. Bueno? The green function, so the green negative, is saying take x and change it to become negative x. So what that means is this is no longer x squared. This is now negative x squared. This is no longer x. This is negative x. That's mathematically what's happened. If you look, none of your answers are there, right? Like, that's not the answer because we're gonna have to simplify that. But before we get into simplifying that, I just want to like make sure that you're okay with where those negatives are coming from. I've tried to color code it, right? So this red one meant multiply everything by a negative. When it was inside the brackets, it meant you actually change x to be negative x.
Yeah. Are you multiplying the whole thing by a negative because it's in front of the f in the other equation?
Mm-hmm.
And the f is on the other side of the equal sign?
Yes. So I'm saying like this is f of x. So if I wanted to put a negative in front of this, I'm also putting it in front of that. Like that's where I'm getting this new equation from. Notice that I didn't write f of x equals here. And I didn't go f of x equals because this is no longer f of x. I've changed it now, right? I'm doing things to it. This was the original f of x. I'm changing it. That's why I didn't go f of x equals. If you've put f of x equals all that, that's fine. It's no big deal. But I've changed it, right? So it's not f of x anymore.
Why aren't you putting negative f of negative x equals?
Sorry, go ahead.
Like you have g of x equals negative f.
Yeah, you could definitely do that.
Like you put that in front of there.
Yeah, you could definitely do that because that's what I've done, right? I've created g of x. They told me that g of x would be a negative in front of the function and a negative in the x spot. G of x is a negative in front and a negative on the inside. Yes.
That's all I was wondering. Why don't we have an equal sign?
Yes, and I purposely didn't put one there yet. Yeah. Logs are easier.
They make more sense. Yeah, really better.
Okay, do we have any other question about where these negatives came from? All right, let's simplify it. If I was to simplify this, I do inside the brackets first. Okay, so inside those big red brackets, I'm not going to deal with this negative. I'm just dealing with inside those big red brackets. You don't have to do it this order. This is just how I would do it. You could do it the other way too. So see if you get the right answer. Don't erase yet. If I was simplifying inside the brackets, first thing I would simplify is negative x squared. If you have a negative thing that is being squared, the negative is now gone. So that would become 4x squared. Right? The squared would go to the negative. Negative squared is positive. It is now 4x squared. The next thing I would deal with is I have a 3 times negative x. That would then just be minus 3x. And the minus 5 has not changed. So the squared went to the x and to the negative. That means the negative is now gone because negative squared goes away, goes positive. That's why that's gone. This negative multiplied by the 3 to become minus 3x. Then I can take this negative outside the brackets and I can distribute it into the brackets. So it goes and changes every symbol. G of x equals negative 4x squared plus 3x plus 5. Hopefully our answer's there. G of x is C. Did you get it? Yeah. I know you did it a different way.
Well, I should have done it the other way because it makes more sense to create the negatives.
I think so. But you could do it first. Do you have a question about what we just did? Everything. Just everything.
It's so mixed up that you're not sure where it goes.
Yeah, and so like today we're gonna do inverse. So we're gonna start this. If we should finish today, tomorrow we're going back and we're gonna do every type of transformation again. So we're gonna combine them, and so you'll see all those examples together. which will be probably good for those like, what is that? How do you go from this to that? Like that is hard. We are going to do a little bit of it here too, but with inverse, it's a little bit weird.
Is the quiz on Wednesday?
Our quiz is going to be Wednesday, and then our plan is to have that unit test for Friday. So you got a week to get that practice booklet done. So if your name is Rowan, you should probably start your practice booklet. Okay, let's talk about inverse. We've actually talked about this before. We talked about inverse in Unit 1. I'm just going to make this like clear right off the bat. The inverse means X and Y switch. And remember when we did inverses, because we graphed, I believe, exponential and then logs, which are inverses of each other. And remember, we just took everything that was X and we made it Y, and everything that was Y and we made it X. So for instance, when we had domain and range, X and Y, we just switched them. When we had asymptotes, X and Y, we would just switch the asymptotes. Like everything switched. X intercepts became Y intercepts became X intercepts, right? Everything X and Y switched. Perfect. Let's do that. So this line that is there is Y equals 2X minus 1. Y equals 2X minus 1. Boom, right there. Perfect. Let's graph the inverse of that function. This would be the inverse. Notice that X and Y have swapped. It's the same function, but I put X where Y is and I put Y where X is. I switched them. Cool. To graph that, this X equals 2Y minus 1. I have no idea how to graph an X equals equation. I've never done that ever, right? The only thing we ever known to do is graph Y equals functions. So to be able to graph this, you need to isolate Y. So you need to get Y by itself. So looking at that function, that means I move my 1 from the right side to the left side. That's X plus 1 equals 2Y. I don't know. They're watching some video. It'll be done soon. They watched it a few times. It sounds like mice.
Yeah.
So I took the 1, I moved it from the right side to the left side. Now I need to get rid of that 2. I divide by 2. Now you could write that as X plus 1 divided by 2, or you could divide each thing individually by 2, like kind of to each their own. So what I mean by that is like you could do this, X plus 1 divided by 2 equals Y. Like that would work. Or you could write it like this, X over 2 plus 1 over 2 equals Y. And those are equivalent. Oftentimes we write it like this because it looks better. This is going to be more beneficial to us. That's why I've changed it. The reason this is more beneficial to us is I can graph that easily because that's in Y equals mx plus b form. So a throwback to math 10. Y equals x plus b. This thing is your y-intercept because it's your constant. This thing is your slope, meaning it tells you the rate at which you're increasing to get to that next point. So by having it in this form, I could easily graph it. If you didn't remember that, you got your calculator. Throw that in your calculator and graph it. All right? You could throw in your calculator x divided by 2 plus 1 divided by 2. And you could graph this equation. Either way, you should end up with a line that looks like this. You're going to have a y-intercept at 1/2. positive 1/2, correct? Yeah, right here. And then you're going to go down by 2. No, rise over run. Up 1/2. Did I miss a negative somewhere? No. Okay, that's good. Up 1/2. Something like that. My line should look like this. And I'll give you some key points for when you draw it. Just copy that. So key points that I have. My y-intercept was at 0.5. Okay. Another key point I have is I do cross through 1, 1. Okay, that's not going to be a coincidence, so make sure your line goes through 1, 1. And then I did have another point here at 2, 1.5. That's from my rise over run. I had gone up 1 unit and over 2 units, which is how I got that point. If you take a straight edge, you should just be able to connect those dots and get that nice, beautiful straight line. You should have arrows on the end of it because those graphs do technically go forever. So throw some arrows on the end of your line. Looks like that. Yep. Yep.
So if we were allowed to, we could have just written down the points like how we did last week's actions. Went up the second.
Yep. So you did like a table of values? 100%. Yep. So if you wanted, like she's asking before when we were graphing things by hand, we just made a table of values, right? When x was 1, y equals something. When x was 2, y equals something. And then you can just plot those points and graph it. That'd be perfect. Cool. Let's talk about visually what's happened. Because that purple graph is the inverse. Okay, it is what happens when you have x equals 2y plus 1. X equals 2y plus 1. Yeah, sorry. Minus 1. Not that you can see it in that like shaded area that I wrote it, but that's perfect. Okay, visually, something has happened. We have a reflection here. So if you drew an imaginary line called the x equals y line or y equals x line right here. This red graph, I'm going to call y equals x. What's visually happened is this black line has reflected to the other side of that diagonal line. You see that? Like if I took this and I folded it to the other side, it's on there. If I took this and I folded it to the other side of this red line, it's here. So the inverse is actually a reflection. When you inverse something, you change the x and the y values, which causes this to happen, where you get a reflection about the line y equals x. I'm going to write that. Reflection about the line y equals x. Cool, right? We had talked, I think, last week about could you reflect about other things? Because we talked about reflecting over the x-axis and the y-axis. I said, yeah, you could. Like, you could reflect over anything, technically. This is a situation where you've reflected about y equals x. You could reflect about y equals anything. The reason that line is called y equals x is because it's all the points where y and x are the same value. So notice that it starts at 0, 0. And any point on this line, x and y are the same thing. -1, -1. -2, -2. -3, -3. Same way if you go positive. 1, 1. 2, 2. 3, 3. It's where x and y are the exact same thing. That's why it's that nice perfect diagonal line. Yeah.
So you could reflect over negative x.
Yeah, you could reflect about negative x. You could reflect about like y equals 7. You could reflect about anything. You could reflect, I guess, technically among like another equation. You could reflect like on the other side of y equals 2x plus 3 or something like that. We don't do that, but you technically could reflect about anything. And some of those examples I gave are above my head, so I don't know. Awesome. The last bullet there on the bottom says determine the location of the invariant points. Invariant. Right? Vary means change. Invariant means doesn't change. So which point does not change? 1, 1. The reason it doesn't change is because that's where y and x equal each other. So if you swapped 1 and 1, it would still be 1 and 1, right? So the invariant point is the point 1, 1 because come on computer, because that is where x equals y. I mean, just put in brackets. They are the same. And this is what I mean when I talk about inverse and like remembering the foundation. The foundation of an inverse is x and y have switched. That's the foundation of everything that happens in an inverse. When you forget that, it becomes hard to do inverse questions. If you just remember, inverse means x and y switch. You'll be golden. So where's the invariant point? Where does it not change? Well, if x and y are the same and they change, that wouldn't change. Right? It'd be the same thing. So invariant points are when x and y are the same. Cool. Let's do some nice notes about how we write inverse. So there's 2 ways that we write inverse. Way number 1 is like this. They take your function notation, which is normally y equals f of x. Normally. And they switch the x and the y. By switching the x and the y, they're telling you that's an inverse, because that's what inverse does. Switches x and y. There's a second way that they show inverse, like this. They go f, and then they give a little -1, like a -1 exponent. There's a difference. These 2 things do mean, there's a reason there's 2 different ways for it. Both mean inverse. Both mean inverse. The difference is that this might not be a function. This, if they wrote it as f of -1, it must be a function. Because inverses reflect in such a unique way, sometimes when you do an inverse, you actually don't create a function. You create something that would not pass the vertical line test. And sometimes when you do an inverse, it does create a function. If it's written like this, it must create a function. That's why it's written that way. If it's written like this, it might be a function, it might not be a function. There's saying it has to be a function. So it could create something that fails the vertical line test. Cool. How can we tell if something is going to become a function or is not going to become a function without going through the hassle of actually doing the inverse? We're going to do something called the horizontal line test. This is where I'm going to cut off the video because it's negatively affecting us so much up here. So bye, Erica.